Now we are going to discuss another problem on the Gauss Divergence Theorem about a cube. So here the verification is asked, verify Gauss Divergence Theorem for f bar is equal to x cube minus yz I bar minus 2x square y j bar plus z k bar or taken over the surface of the cube bounded by the lines x is equal to y is equal to z is equal to a and the coordinate planes. So before we go to the solution, we will understand the given question. Verification is asked for divergence, so you have to show LHS is equal to RHS. F bar, it is already given in the form of a vector equation I, J, K, and it is given about the cube. So on the cube, the plane equations are given as x is equal to y is equal to z is equal to a and the coordinate planes. You have to understand that coordinate planes are nothing but x is equal to y is equal to z is equal to 0. You are supposed to take it directly. Either the values can be given equal to 0 or in the words it will be mentioned as coordinate planes. Moving to the solution. F bar is given as x cube minus yz I bar minus 2x square y j bar plus zk bar. This is the given equation, and we said that coordinate planes we are taking as x is equal to y is equal to z is equal to 0, and the plane equations are given as x is equal to a, y is equal to a, z is equal to a. Whatever the plane equations are given to us, we will be converting in the form of limits here as x tends to 0 to a, y tends to 0 to a, z tends to 0 to a. Now you draw a figure of a cube with 6 faces on your x, y, z axis here with respect to the origin point. Now coming to the statement of divergence theorem, it will be given as surface integral f bar dot n bar ds is equal to volume integral divergence of f bar dE. Now I am going to first make it the surface integral, then I am going to make it the verification of volume integral here. So surface integral we have taken as I is equal to surface integral f bar dot n bar ds. Either you can make it as n bar or n cap. Now here we know that the cube will be having 6 surfaces. So the surface integral we have divided into the 6 surfaces here as integral S1 plus integral S2 plus integral S3 plus integral S4 plus integral S5 plus integral S6. F bar, it will be common for all the 6. Since f bar is common for all the surface integrals, n bar, it depends upon the face on which axis you have taken. On that particular base you are going to substitute n bar. Coming to the ds value, based on the axis you are going to choose the plane equation. That plane will be converted in the form of ds value. So here for our convenience we have taken all the surface integrals as I1, I2, I3, I4, I5, I6. Now you are going to make it I is equal to I1 plus I2 plus I3 plus I4 plus I5 plus I6. Now we are going to give I1 on the face on positive x-axis. From the figure I am explaining all the surface integrals, how we have taken positive and negative x-axis, y-axis, z-axis. Coming to the figure, for positive x-axis, C is the point of intersection. You form a closed loop, start with the C and again you end with the C. When you are making the positive x-axis, you see that that particular diagram should not touch your y-axis and z-axis here. So your point of intersection is starting with the C. For positive x-axis, form a closed loop here with 4 vertices C, D, H, B. Again you will be ending with the same vertex as C. It is not touching your y-axis and z-axis. This is the positive x-axis face. Moving to the negative x-axis, every time for the negative values, negative axis, you start with origin. And you see that that particular axis should not touch your intersection point of the positive axis. So here we are taking negative x-axis. So this negative x x-axis point should not move to the positive x-axis. In such a way, the closed loop should form. And you see that origin on negative axis, when you are starting, it should touch the other two axes as y and z. So your closed loop will be 0, E, F, A. It is touching the y-axis and z-axis for the negative x-axis. This is the phase for negative x-axis. Moving to the positive y-axis, your point of intersection is starting with E. Again, it should form a closed loop with 4 vertices here, E, F, H, D. And again it is ending with your same point of intersection. It is not passing through the remaining 2 axes here. It should not touch the origin also. Coming to the negative y-axis, again you will start with the origin. For the y-axis, you are having opposite axes as z and x. The negative axis should pass through z and x axis. In such a way, you are going to form a loop here. So here, you will start with origin. O, A, B, C will be the negative y-axis phase. Coming to the positive z-axis, your point of intersection is A. So you start with A, form a closed loop. It should not pass through the origin and it should not touch the remaining axis of x and y. In such a way, you have to form a figure with the 4 vertices A, D, H, F. This is for the positive z-axis. For the negative z-axis, again you will start with origin and you are going to see that for z-axis you are having x-axis and y-axis as the opposite variables. So you have to see that negative z-axis should pass us through the positive and negative, should touches your x-axis and y-axis. So you are going to form a figure as O, C, D, E as the negative z-axis phase. So I have converted these phases in the form of I1, I2, I3, I4, I5, I6. Now you are going to find out the first phase here, I1. So on I1, we are going to the phase CDHB on positive x-axis. On positive x-axis, outgoing vector is I bar. On positive x-axis, YZ will be the plane. So you are going to take it YZ as the surface area and you will be converting as ds is equal to dy dz. Since you are integrating with respect to y and z, you are taking the y limits and z limits which was already calculated in the beginning itself. So y limits are 0 to a, z limits are 0 to a. And you are going to take on positive x-axis the line equation as x is equal to a. This can be substituted in your integration if necessary. So you are going to make it the surface integral as I1 is equal to surface integral S1 f bar dot n bar ds. F bar it is already given in the question as x cube minus yz I bar minus 2x square y j bar plus z k bar. Using dot product n cap, you know that it is I bar on positive x-axis. ds is converted as dy dz. On substituting your dot product, we got the equation as integral 0 to a x cube minus yz dy dz. On integration with respect to y and z, you got here x value. Since you have got x, we are substituting x is equal to a on positive x-axis. You substitute x is equal to a and apply the integration y and z. Since y limits and z limits both are constant, you can integrate any one of the first value followed by the second value. On simplifying your integration, we got I1 is equal to a power 5 minus a power 4 by 4. In the same process as we have done for I1, you will be calculating for I2, I3, I4, I5, I6. All the surface integrals of a cube, you on simplifying, you will be getting your last I values. All the I values you are going to get. Add up all the I values substituting in your equation 7. You got I value is equal to a power 5 by 3 plus a cube. Since there is no time to explain all the video, all the terms, just it was already explained in the surface integrals. If you are having any doubt, you can check through the surface integral. In that I have clearly explained how to calculate I1, I2, I3, I4, I5, I6. Same process here also you are applying. As we have explained I1, it will be followed for all the remaining cases. Based on your axis, you are going to take it the outgoing vector positive, negative on that particular plane. So moving to the RHS value. So RHS we have taken as I is equal to volume integral div f dv. So divergence of f bar is nothing but del dot ef. So dv is equal to we are taken as dx dy dz. So you are going to substitute divergence f bar as del dot ef. We know the value of del and f bar it is given by applying the dot product and applying the respective derivatives in the volume integral. On simplification, you will be getting as 3x square minus 2x square plus 1. On simplifying, we got x square plus 1. So here we have taken the limits for the volume integral as the x value as 0 to a, y limits as 0 to a, z limits as 0 to a. It was already simplified in the beginning itself. Now here, since all are constant limits, then you can integrate any one of the first value. Here I have calculated first with respect to x, then followed by y, then followed by z. Whenever you are getting the integral limits as constant, you can make it according to you can make it any one of the first value, then followed by the remaining two integrals here. If you are having variables, then you have to eliminate the first variables, then followed by constant terms. So on simplifying this total integration with respect to x, y, z, we got I is equal to a power 5. So a power 5 divided by 3 plus a cube, which is already in the LHS you got in the surface integral. Same value we got in the RHS for the volume simplification. Therefore, you can say that LHS is equal to RHS. Then you can say divergence theorem is verified. Because of due to the shortage of this video, I am giving only roughly the question was explained. If you are having any doubt, you can check your previous video of surface integrals and volume integrals. Same process was applied here. There we have applied in the single way. Now here we are clubbing both the integrals, surface and volume. Both the integrals were clubbed and LHS and RHS when we have simplified.